Hi everyone, my name is Guanyu from Jinan University. Today I'm going to talk about effects of postures or identifying usual for selection-based behavior authentication in virtual reality. Posture switching is very common when using VR devices due to fatigue and other factors. Previous studies show that in both the real world and VR environments, usual behavior differs across postures when performing tests such as tapping, locomotion, gaze, or selection. However, existing behavior authentication rules such as target selections and slowing-based authentication does not fully consider the negative impact of posture switching on authentication systems. More specifically, in common selection-based authentication systems, the model is trained with samples collected in a seated posture during enrollment. However, during later authentication, the users may log in while standing. Behavior differences across postures may reduce system accuracy. On the other hand, if this negative effect truly exists, how can we address it? If real-world deployment of behavior authentication, users often enroll on one day and log in on another, so I will focus on three questions. First, if enrollment and login use the same postures, how do different postures affect selection-based authentication accuracies? Second, if enrollment and login use different postures, how does posture mismatch affect accuracies? Third, can matching data from multiple postures improve accuracy? We recruited 30 participants, all of whom were right-handed, including 15 females and 15 males. Each participant will receive a $5 reward. We used an HTC Vivo Pro VR handset with a 90 refresh rate. The chair we use supports backrest adjustments from 90 to 160 degrees, and it could both rotate and slide. We test three common postures: standing, sitting, and reclining. These postures had different backrest tilt angles. For interaction tests, we designed a standardized selection test. This test is widely used in behavior authentication. It covers different layouts, target size, and target distance. This video shows how we collected the user data. We mainly record the behavior trajectories generated during target selection. In real-world use case, where users may log in across different days, our data collections included two sessions. The first session collected registration samples, and the second session collected login samples. The gap between two sessions was at least 24 hours, and each session provided 4 repeat samples. The total experiment time was about 2 hours. We chose 4 common time series algorithms as our models, and we use communication time, classification accuracies, and NASAs as our evaluation metrics. In addition, our biometric features were collected from the HDM and the two controllers. The feature types include position, rotation, linear and angular velocities. Furthermore, to ensure fair comparisons across conditions, we apply standard pre-processing. These include initial position alignments and linear interpolation. In the next step, all collected data was divided into training and testing sets. The training sets included only samples from session 1, while the testing sets included only samples from session 2. In addition, 3 experimental groups were defined. The first was within postures group, where training and testing were performed under the same posture. The second was the cross-posture group, where training and testing were performed under the different postures. Third, we defined the master posture group, in which the training sets included multiple postures. In this group, if the training set included the postures used in the testing set, we label it the MI group. Otherwise, we label it the ME group. In addition, when the model was trained using samples from all postures, we label it the O group. This figure shows the result of algorithm comparison. We found that the Rocky algorithms perform best on our datasets, so all subsequent analyses are based on Rocky. This slide shows the result of communication time and NASA. We found that posture significantly affects communication time. Reclining is slowest, sitting is moderate, and standing is fastest. In addition, communication time is influenced by both distance and vertical position. Consistent with this, the NASA results indicate that standing requires greater efforts and physical demand, whereas reclining is less physically demanding but more time demanding. Overall, posture impacts both objective performance and perceived workload. This slide breaks down the within posture result in more detail. We can see that the posture transfer time clearly affects classification accuracies. Reclining performs best, sitting is in the middle, and standing performs worst. Vertical offsets also make differences and it actually interacts with postures. For standing and sittings, negative 30 degrees give the best accuracies, while for reclining, 0 degrees works best. Overall, this suggests that the best target position depends on the posture. This slide shows results of the cross-posture group. First, classification accuracy dropped clearly in the cross-posture group compared to the within posture group, which suggests that posture mismatch reduces accuracies. Second, posture transfer time has a significant effect on accuracies. In particular, sitting as a bridge. Transfer from sitting to standing and from sitting to reclining perform better, whereas standing to reclining perform the worst. Finally, posture transfer time also interacts with vertical offsets. For example, for standing to sittings, the lower target position often works better. In contrast, for sitting to reclining, the centers and upper target position can perform better. Overall, posture mismatch and spatial offsets both influence classification accuracy. This slide shows the result of the mass posture group. We found that the mass posture group performed better overall than the cross posture group. This suggests that training with mass posture can improve the model's robustness. Moreover, in the ME group, training with standings and reclinings and testing on sittings give the best accuracies among posture transfer types. This shows that a good sample mixing strategies can improve classification accuracies even without target posture data. Finally, we found that increasing the number of mixed samples can further improve models' robustness. We can apply our findings on posture effects to common VR scenarios. For example, in situations where posture is stable, like drawing simulation games, posture-specific models are enough. But in scenarios where people frequently change their postures, such as in a VR home office, we need to take posture variation into account to improve model robustness. In the first use case, we can design the target selection layouts based on postures. For example, when users are standing or sitting, placing targets slightly below the gaze lines tends to improve accuracies. However, when users are reclining, it works better to put target closer to the gaze center. In the second case, our finding can guide the selection of optimal posture combinations. This helps reduce the cost of data collections and improve model generalizations. For example, if we want to transfer to the reclining postures, we should collect sitting data rather than standing data. In another example, when it is difficult to collect data for target postures, we can still improve generalization by collecting data from another posture. Finally, I'd like to talk about limitation and future work. First, we still need long-term evaluation because user behavior may change over time. Second, we should include older adults as well, since postures and interaction patterns can differ across age groups. Third, we plan to develop cross-posture algorithms so that the model can generalize better across different postures. That's all. Thank you for your attention.